Now you can see it, hopefully. So chemical equilibrium, again, involving these reversible reactions, where we do have those kind of two directions, the forward direction and the reverse direction. Put my E there and see if it froze. That's good. All right. And again, as we talked about, remember that when it does reach chemical equilibrium, we're really not talking about, sort of the amounts on both sides of the arrows, but we are talking about the rate of the forward direction equaling the rate of the reverse direction. So that's what it means when it reaches chemical equilibrium. The sort of consequence of that, as we were talking about, is pretty much whatever their concentrations are, the reactants and products, or whatever their pressures may be if we're dealing with gases, again, they will pretty much maintain those concentrations or pressures because just as quick as it goes one way in the reaction, those products will recombine and kind of come back the other way. And again, it just locks everybody into place. Again, not necessarily the same amount on both sides of the arrows, but we will have everybody maintaining it as long as you don't do anything to screw the equilibrium up. That brought us to the equilibrium constant expression, and we talked about it really being the concentration of our products divided by the concentration of our reactants. And remember that one of the nice things about K is it's really just a number. And what that number allows us to understand is if we have a large value for K, that means when we do reach equilibrium, we would mainly expect products to be present. And if we have a small value for K, when we do reach equilibrium, we would mainly expect to have reactants that are present. Just mathematically speaking, that's basically what you end up with. When we do write the equilibrium expression, a reminder that we do take the coefficients from the balanced equation into account, and they do become the exponents when we do that. So our equilibrium expression here would look not like that, if I'll get the right letters there. So C and C, D and D. So that's our products over our reactants. And as we talked about, when we write something like this that involves concentration, this is also sometimes referred to as the Kc expression. C obviously being for concentration. And again, as we talked about, that would be molarity, so our moles over liter in most cases. We could also write a Kp expression if we are dealing with gases. Works the same way. It'd be the partial pressures, though, of our products over our reactants. So that'd be the partial pressure of C times the partial pressure of D divided by the partial pressure of A and the partial pressure of B here. Now, Kc and Kp really do not necessarily, most of the time, equal the same numerical value, but they do give you the same information. So if you have a small value of Kp or Kc, that means, again, you mainly have reactants at equilibrium. And if you have a large value of them both, you do have mainly products. Now, in certain cases, we can't go from one to the other by using the formula that we saw, Kp equals Kc RT delta N. And the Kp is obviously our equilibrium expression involving pressures. Our Kc is the one involving, obviously, concentrations. Our R's are gas constant, 0.08206. And our temperature here does need to be in Kelvin. And as we also talked about, really important when you do that is the delta N part of it. You just don't want to take the difference. You do want to do products minus reactants, as it may give you a negative number, which is important if, obviously, mathematically speaking, how you would actually solve it. Now, the value of K, as we talked about, is an equilibrium constant, which means it is a constant value for a particular reaction at a particular temperature. And it does not matter how much you start with in terms of reactants or products. Again, if you ran it at a sort of a constant temperature and you started with all reactants, it will come to the same ratio of products to reactants. If you ran it at the same temperature with less reactants to start with, some reactants, some products, it will always reach really the same ratio of products to reactants. The only thing that will affect the numerical value for the equilibrium constant is actually temperature. And when we talk about that is if we took the K value at, say, 25 degrees Celsius versus the K value at 40 degrees Celsius, these K values here would be different values, numerically speaking. But if you did a bunch of reactions at 40 degrees Celsius, they all should end up being the same K value when you calculate them. Or if you did them all at 25 degrees Celsius, they should be the same value. Again, if you went from 25 to 40 and compared those two at the different temperatures, you would see a different value. We also talked at the end ways to manipulate reactions and how they affect the K values. Remember that if you add some reactions together, you're going to actually multiply the K values, not add them. If you need to multiply a reaction by a common number, you then take basically the K value to that common number. Like, for example, if you multiplied by 2, you would then square the K value. If you multiplied by 3, you would cube it. And if you had to divide a reaction by a common number, you would actually take the root of the K value to that common number. So if you divide it by 2, you take the square root of the K value. If you divide it by 3, you take the cube root of the K value. And the last thing that you can do to the reaction is you can reverse it. When we do actually reverse a reaction such as these, what happens to the K values actually becomes 1 over the equilibrium constant. So it basically becomes the inverse of it. We don't change signs. It's again becomes 1 over it. Any questions on any of that there? All right, so I think where we laid up last time was here. You were supposed to finish that. I'm gonna hope you did. We'll see here, I guess. So in this case, we're looking for really the K value for this particular reaction here. And we really sort of, again, want to kind of build it from these two. So again, if you didn't take 200A here, you might have done something called Hess's law in 200A. If you took it here, we'll do it later on. But you're basically just going to build these reactions. And really the easiest approach is just to try to make sure everybody's on the correct side and make sure that you have the correct amount of everybody. So for example, here, I could start with E. And I see that I need E actually on the left-hand side, but E in this equation is on the right-hand side. So I do need to reverse that reaction to get it to the left-hand side. In addition, I don't need 1 E, but I actually need 2 E's. So for this particular reaction here, we actually need to reverse it to get everybody on the correct side. And we also need to multiply by 2 to get everybody on the right amount. So when I do that, that will give me 2E plus 2F goes to 2C plus 2D. Now, in terms of the K value, we did a couple things. First off, we reversed it. So we are going to take 1 over the K value. And then we also times it by 2, which means we then will square the K value that we got left over at that point. So the 1 over K is because I reversed the reaction. The 2 up there, the squaring part, is because I also multiplied by 2. So that's something like 1 over 20 squared, I believe. Any questions on that there? Now that takes care of getting E to the correct side. That also takes care of getting F to the correct side. So the next thing I want to look at is A. A is on the right-hand side. In the first equation, A is on the left-hand side. So I do need to reverse the first equation. And that's really all I need to do on that guy. So I'm going to reverse it, which gives me 2C plus 2D, A plus B. Now, because I reversed that, that's going to mean that the K value now for this reaction will be 1 over K. And I'll just go underneath it here. That would basically be 1 over 100 in this case. Any questions on that there? Now, if I did this correctly, when I add these together, everybody should cancel out correctly. So 2C will cancel, 2D will cancel because they are opposite sides of the arrow. At this point, everybody on the left-hand side should stay there. And everybody on the right-hand side of the arrow should stay there as well. And I did build the equation that I'm looking for. Any questions on that there? So we'll call this K1, call this K2. So to find the K value here, we do want to take K1 times K2, the adjusted values. So again, for the first reaction that we played with there, we reversed it, which means it's going to be 1 over 20. And then we also times it by 2, so we got to square it. That gives us 0.0025 when we do this guy here. We also reverse the other equation, which is 1 over 100 gives us 0.01. So those are really the numbers here we're going to multiply. And if we do that, 0.0025 gives us a K value for this guy. Of 2.5 times 10 to the minus 5. Any questions on that one? So it's important here to just make sure everybody stays on the correct side. Also, it's important to keep track of what you did to each of the individual equations so that you know how to manipulate the K values associated with it. Any questions on that there? So hopefully that's what you got when you did it at home over the weekend. All right, let's try another one here just to make sure. So try this one. We'll pretend it's reversible reactions, even though they're really not, but we'll pretend in this example here. So we're looking for what is the K value for this equation. Once again, using these equations here and this made up, not realistic equation. Okay, let's take a look and see how you're doing. So again, the easiest approach when you're doing this is really just to make sure, again, everybody's on the correct side. You have the right amount of everybody. So for example, here in the equation I'm looking to end up with, I got N2 on the left, which I do here, but I do need 2 of them. And up on top there, I only have a half actually. So I do need to actually multiply this by 4, I believe will get me there. And that will get me 2 of the N2 plus 12 divided by 2 is 6H2. Will give me 4 of the NH3. Now, in terms of the K value, because I multiplied by 4, we then will take the K value to the 4th power here. Any questions on that there? Looking at the second equation here, or really even the one we're trying to build, I need water on the left-hand side, which it is, but I do need 6 of them. So that is going to require us to multiply the bottom equation there by 3. When we do that, we end up with 6 waters, 6 H2O on the right, and 3 O2 on the right-hand side. Once again here, because I did multiply by a common number of 3, I am then going to cube my K value, not multiply by the K value. So I'm just going to cube it. And again here, if I did this correctly, everything should cancel out that needs to. So we have 6 H2 on the left and 6 on the right, so they will cancel. And I think that's it in this case. So everybody on the left stays on the left. So that's 2N2 plus 6 H2O goes to 4 NH3 and 3 O2, which is the equation we're looking for. Now, once again here to basically figure out the K value for this guy, we're not going to add, but we are going to multiply our adjusted K values together. And that would give me 411 to the 4th power times 0.345 cubed. And that gives me a big old number. All right, so that is, we'll call it 1.17 times 10 to the 9. That's a pretty big number there as our K value for this equation. Any questions on that there? So you do need to know how to do this, obviously. And it may come up in other chapters where you may need to manipulate some equations and need a K value to use. So again, it commonly does. Any question on any parts of that there? All right, so when we do write our equilibrium constant expression, as we've been talking about, again, it is usually expressed in concentration as molarity. I think I might have mentioned it earlier as we were talking, but typically speaking, you do want pressures to be in atmosphere. Again, that's sort of the standard unit, especially later on here when we start talking about solving some equilibrium pressures and stuff like that. And again, even if the problem does give it to you in some other pressure unit, you typically do need to convert it to atmospheres, do the calculation, then kind of go back to whatever unit they may want. As we talked about, we do not include solids or liquids in the equilibrium expression. So that really does leave us just two things, which is aqueous or gases that do go in. Again, it doesn't have units. And when we do see an equilibrium value, constant value, it is specifically for how that reaction is written. What's the reactants, what's the product? So it is specific for that. And obviously, if we do some adding of individual reactions like we've been talking about, we do multiply the K values together. And again, this is some of the other stuff that we were just talking about. If we have to multiply, we take it to that power. And again, if we have to sort of divide, we take it to that root. And if we have to reverse a reaction, which is commonly done as well, 1 over the K value is how we get to that new equilibrium constant expression. As I mentioned before, and it is sometimes hard for a lot of people to sort of visualize that or understand that, is the idea of, no matter how much you start with, as long as you keep the temperature the same, you will get the same value for the equilibrium constant, which is Y is constant. I think I did the math example the other day. And again, there's many different ways we could divide to get to 2, so it's kind of the same idea. No matter what we start with, although our reactant concentrations may be different than our products in different experiments, the ratio of the products to reactants will always end up being basically the same idea or the same value, as long as you keep that temperature the same. So as we talked about there, any questions on that there? So the next thing we're going to talk about is a break for K for a second here and talk about a different letter of the alphabet, which is Q. And Q is the reaction quotient. And really, Q is used for a couple of situations that we will see. One situation, I kind of call it just a straight up Q type question. And that is a question of, you're given some concentrations of everybody, or even you're given some pressures of everybody, and you're not sure if you are at equilibrium or not. So that is traditionally what the reaction quotient is used for, to help you determine, are you at equilibrium or are you not at equilibrium? And that would be a situation, obviously, where you are given information about everybody in the reaction. Reactants, products, you could calculate Q. How do you calculate Q? Q is calculated the exact same way as K. So Q is calculated the same as K. So Q is the concentration of your products divided by the concentration of your reactants. And just like what you do with K, you still take the coefficients as the exponents. So essentially calculated the exact same way as you do K. The only difference is you're not really sure if you're at equilibrium or not. So one of the things that it will tell you is that question, are you at equilibrium or not? But the second thing that it will actually tell you is if you are not at equilibrium, it will tell you which way you need to go to actually reach equilibrium. Do you need to continue to make more products? Do you need to continue to make more reactants? So it will tell you, hey, you're not at equilibrium, but you need to head to the left there and make some more reactants, or you need to head to the right and make more products. Or it will tell you you are at equilibrium, obviously would be the other choice. So Q calculated the same as you do K, again, using those coefficients as those exponents. And if you calculate Q and it is less than the Kc value, you are not at equilibrium. And in order to make or reach equilibrium, you actually need to make more reactants. So if you line up Q on the left and K on the right, it goes opposite of where that is pointing. So you need to make more reactants. If you calculate Q and it equals the Kc value, then you're at equilibrium. And if you calculate Q and it's less than the Kc, you actually need to make more products in that case. Again, basically opposite of where it points. The only way that you could calculate Q is if you're given the information about everybody in the reaction, because there's no other way to do it. So that is definitely a situation where if you come across a problem and you're given the concentrations of everybody or the pressures of everybody in the reaction, you should stop and actually calculate Q and see if you are at equilibrium or not. And more importantly, as we'll talk about later on, if you're not at equilibrium, it'll allow you to know which way you need to go to actually reach equilibrium, which could be important in terms of calculations that we continue to do. So Q, reaction quotient, used to determine whether or not you're at equilibrium and which way you need to go to reach equilibrium. Any questions on that there? All right, so let's try one here. If at the start of the reaction, you got 0.249 moles of N2, 3.21 times 10 to minus 2 moles of H2, and 6.42 times 10 to minus 4 moles of NH3, and they're in a 3.5 liter vessel, and the Kc value is 1.2, are you at equilibrium? And if not, which way do you need to go to reach equilibrium? So take a few minutes here and calculate it up. Now, is this system at equilibrium? And if not, which way to go? The reason we can obviously calculate Q is, although we're not given the molarity of everybody involved, we are given the moles of everybody that's involved here, along with the volume. So that does allow us to calculate the molarity of everybody. So we do have really the concentrations of everybody, which would imply obviously this reaction is going on, or we dumped everything in at once. So we do need to see if we are at equilibrium. So we do want to calculate Q. And once again, Q is calculated the exact same way as you would do K. So it would be our product. So it would be the concentration of NH3. And just like we do with K, we will have to square it because of the coefficient. That would then be divided by the concentration of N2 times the concentration of H2. And once again here, we will cube it because of the coefficient that's in there. So basically the exact same way as you do K, exact same rules. If it's solid or liquid, you leave it out and you don't deal with it. So obviously just gases and aqueous. Any questions on that there? So obviously to put our concentrations in, we do need to calculate it. So might as well do that first. So the concentration of N2 should be our moles, which is 0.249. Divided by our volume, which is 3.50 liters. And that gets us 0.249 divided by 3.5. That'll give us something like 7.11 times 10 to the minus 2 molar. We'll do the same thing for our H2. So the concentration of H2 will be the moles of H2, which is 3.21 times 10 to the minus 2. And that would be divided, and those are moles, divided by 3.50 liters. 3.21 to the negative 2 divided by 3.5 gets us 9.17 times 10 to the minus 3 molar. A reminder, I don't know if we talked about it or not, but just so everybody remembers, hopefully there is a exponent button, right, on your calculators that you should be using. Looks like an EE button, EXP button, some of the fancy new ones. I don't know if they're fancy or not, but as times 10 to the N, an actual circle type of thing. So one of those three you should be using as your exponent button. So for example, 3.21 exponent button. When you hit that, that represents the times 10 part of the number. So you do not need to put it in. You want to make sure you use your negative button and also 2. That is the proper way to put something in scientific notation to your calculator. If you're using like shift and the log button or the multiplication button to do that, you are doing it incorrectly and you'll be in trouble in this class for sure. So if you're not sure, make sure you come see me. If you have this button on the top right, you do need to put parentheses around each number in my experience. Otherwise, you'll get the wrong answer because of the way your calculator is programmed. Usually they'll take two-tone calculators that have that button. It's kind of like a white on the outside, blue or green sort of base color. So make sure you do know how to properly put these things in scientific notation. If not, make sure you come find me with your calculator and we'll do it. One way you know is usually the exponent part's not good, but the front part of the number is okay. That's usually how you could tell. All right, so lastly here, NH3 concentration would be 6.42 times 10 to the minus 4 moles divided by 3.50 liters. So 6.42 to the minus 4 divided by 3.5. There we go. 1.83 times 10 to the minus 4. And a reminder that your calculator may not give it to you in scientific notation. So you may have obviously 0.000183. I think I got the right number of zeros there. Any questions on that calculation there of molarity for everybody here? Now that I do have the molarity for everybody, we could go into our Q expression and solve. So Q in this case will equal our NH3, which is 1.83 times 10 to the minus 4. Once again, we're going to square it, divided by the concentration of our N2, which is 7.11 times 10 to the minus 2, and our concentration of H2, which is 9.17 times 10 to the minus 3. And once again here, we're not going to forget to cube that guy. All right, if we do that, going to do a little square root, not square, going to square it. Hold off on the square rooting. 1.83 exponent negative 4 squared divided by 7.11 exponent negative 2 and divided by 9.17 exponent negative 3, and that is cubed here. So we end up with something like 0.611 as our Q value. If I converted that backwards, right? First off, any question on that? So now that we have the Q value, we actually want to compare it to the KC value. So in this case, my Q value is less than, equal to, greater than the K. It is less than the K. What that tells us is it is not at equilibrium. And to reach equilibrium, do I need reactants or products? It's actually opposite of where that guy is pointing. So that's to the right, which means we need products here. So we do have to head to the product side to reach equilibrium. Any questions on any of those steps there? So again, that is what I would consider sort of a straightforward Q type problem. And that's usually the question like, hey, are you at equilibrium or not? There is another instance where you should use Q when we talk about the next type of calculation, and we'll touch upon it when we get there. But usually the safe rule is if you're doing some type of equilibrium calculation and they give you everybody's amounts, probably should take a second there and calculate Q. Any questions on the reaction quotient here? Okay, so now we're going to get into really the calculation of the season. Yes, so this is the big calculation that we're going to do here. So when we are not given equilibrium concentrations or equilibrium pressures, a lot of times we're given sort of initial concentrations or initial pressures, and we do need to calculate those equilibrium concentrations. So that does require a certain type of calculation, which is essentially the main calculation that we do throughout the semester. We just sort of adjust it a little bit here and there along the way. So when we solve problems that involve initial concentrations and we're looking to get everybody's equilibrium concentrations, we use what is usually referred to as a ICE table to do that. And ICE means initial, change, and in this case, equilibrium. Now, sometimes you learned about ICE tables when you did limiting reagent type problems. So if you took me, you did, and maybe you could thank me for that now. But maybe you didn't if you didn't have 200A person to do that. But sometimes you do it using for limiting reagent or reactant type problems. But basically, we have an unknown in the nice table, and the unknown is usually represented by the letter X, and that usually represents the change part of the reaction that takes place. So when we do these calculations, basically, we start with a reaction like A plus B goes to 2C or something like that. And we have some initial concentrations, maybe of, say, 4 molar for A, 4 molar for B, and that's about it given to us. Maybe they give us an equilibrium constant that's like, 125 or something like that. So how we would approach this reaction or this calculation is we want to know what is the equilibrium concentrations basically of everybody that is present. So we would set up our reaction, and for the most part, like any sort of equation, it really doesn't work if it's not balanced. So you should always take a good look at it, make sure that the equation is balanced. I will say the good news about our class is usually it is balanced, but not 100% of the time, but probably more times than not, it's going to be balanced. But you definitely want to make sure that it is balanced. If it's not balanced, it will screw up your entire calculation. So make sure you do take that moment just to double check. Now, initially, what we would do is set up this sort of table, and we would put our initial concentrations, which is 4 molar, 4 molar. And now there was really no mention of anybody there on the product side. So if they don't mention anything on the product side, it is safe in pretty much all cases to assume that you have no products to begin with. So you can just zero it out, basically. So those are your initial concentrations. It is also fairly safe to assume that if you do not have any products sort of given to you, that this reaction would probably head in which direction here to start with? Would it go in the forward direction or the reverse direction? It would probably head in the forward direction, right? Because frankly, there's no product, so it can't go backwards, right? Until you make some products. And that's really important for the change part of our table. Now, the change part of our table is really, as it sounds like, how much is changing. And we do represent the change part of our table with the letter X. And because this reaction is going to be heading to the product side, would I expect my reactants to increase or decrease with time? The concentration of reactants should do what if it's going to the product side? It should decrease, right? Because you need reactants to make products. So the amount of reactants should go down. The amount of products should go up. So we represent that change with minuses and pluses. So the reactants in this case would be minuses of X, and the products would be plus X because they're increasing, and that's because the reaction is heading towards the product side. Now, the other super important part, use the word super there, is actually the coefficients in the balanced equation. And you do need to take the coefficients into account when you do the change part, because that takes care of everybody's favorite thing, which is stoichiometry, like the mole-to-mole relationship and all that kind of good stuff. So this would be minus X because coefficient is 1. This would be minus X because the coefficient is 1. Now, when we get to the product side, we're increasing. So this would be plus 2X because the coefficient is 2. Now, if you do not use the coefficients in that part of the calculation, you can mark it wrong yourself because you do not have the right mole-to-mole relationship. So it's really important to do that. And again, if you took me, this should look kind of familiar to you, hopefully at this point. So at equilibrium, what we're actually going to do is just carry down everything that's above it, which would be basically 4 minus X, 4 minus X, and 2X in this case. First off, any question on the ICE table here, how to set up? So a couple of really important things. Again, make sure the equation is balanced. If you do not have products, it's safe to assume that it's going to the product side. And more importantly, make sure that you have those coefficients involved. Otherwise, again, you have the wrong stoichiometry. Yeah. So this does, it does depend, and I would say probably 99% of the problems you come across, even maybe more, It will be negative on the reactant side and positive on the product side. Now, the one exception could happen is what we actually just talked about when we talked about the reaction quotient, right? So in this case, if we were given perhaps starting amounts of everybody, reactants and products, this would be a second situation where you could calculate Q. And if we calculated Q and it said you were not at equilibrium, but to reach equilibrium, you actually has to make more reactants, then which ones would be positive and which ones would be negative in that case? Right. And the other side would be positive. So, and they're sort of, I'll call it a rare case. It doesn't pop up too much, but it potentially could. And that would be a situation where you would want to, again, calculate Q because you're able to do so. And if it happened to tell you you're actually heading to the reactant side, that means really the reverse reaction is going to take place and your products will decrease, which means they should be negative and your reactants would increase in that case and it would be positive. But I would say almost autopilot, you probably don't have to think about it. It's probably going to look like this in probably a majority of the problems, but there are some problems where it's really not the case. So you should be watchful of it. But more times than not, it will probably look something like this where the reactants are decreasing and the products are increasing. Other questions? Okay. So this is where it's going to sort of vary a little bit different from how we used it with limiting reagents, is we're actually going to use our equilibrium expression for this. And if we wrote our equilibrium expression for this reaction, it would be the concentration of C squared, again for the coefficient, divided by the concentration of A and the concentration of B, and that would equal $1.25 in my made-up example here. So the goal of the ICE table is to have us be able to really solve for X. So we really want to figure out what is X equal to. And the way we do that is we use the expression, and because these are technically the equilibrium part of it, we would take these guys and basically put it into this expression. And that would give us something in this example of 2x squared divided by 4 minus x times 4 minus x equals 125. At this point, it becomes really a math problem. We want to solve for what x is, and we'll do some examples, so we won't finish this one, but I want to talk about a couple of different ways, or a couple of common ways that we have to solve this. So basically, you're going to solve for x, and we won't do this one. We'll do one in a second here together and kind of look through it. When we do solve for x, that represents the change part, and the reason why that's really important is once you solve for x, however you solve for x, this x is the x that we see in the equilibrium line there. It's this x, it's every x that you see in this table. And now that we would have a numerical value for x, we could then go back to our equilibrium line and basically calculate the equilibrium concentrations of everybody's there by putting x in for each of them. And that will give us our equilibrium concentrations. So there's a few different ways that you'll come across, mathematically speaking, of how to solve these things. Some may be a little bit more difficult than others. Some may be a little bit easier than others. But one of the most difficult ways for our particular class that we will use will involve just a math reminder, the quadratic. And that is something like x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Hopefully you've seen that somewhere, I hope in a class, right? And this is based off of a to the a plus b to the b plus c. And equals 0. Where this is our values, basically a, b, and c. That is not right. Let me write that right. X squared plus x, a, x squared plus bx plus c. There we go, equals 0. See, it's been a while. I'm a little rusty there. There we go. Like something like that, where the coefficients in front of these guys would be your a, b, and c value that you would put in there. By the way, if we've used the quadratic before, yes. When you use quadratic equation there, you get how many answers? Get 2. And in our case, only one answer will make sense. So when you use the quadratic equation, one of the answers that you get for x, for example, and you put it back into the equilibrium line, will yield you a negative concentration, which obviously you cannot have a negative concentration. So one of them will be good, one of them will be bad, and that's usually how you can determine it. A lot of times you can determine, which one will be good or bad if you end up with a negative number. But just so you know, you can end up with two negative numbers off the quadratic. You could end up with two positive numbers. You could end up with a positive and negative number. But it is actually when you go back and put it into your equilibrium line, it will yield you something that ends up being negative, which then it is not just the greatest choice there. Any questions on ice tables? So we use this when we are definitely not at equilibrium. We use this when we are given initial concentrations, and we use it to help us figure out equilibrium concentrations. Any questions? All right, so let's do one here together to see how it all works. All right, so we're going to roll with this one here. Hope for the best. All right. So in this case, the equilibrium constant for this reaction is 7. And as Br2 goes to 2Br, if the initial concentration of Br2 is 0.663 molar, we want to know what is the equilibrium concentrations of everybody involved. So this is definitely an ice table. I would almost say when in doubt, lay up an ice table. You probably are not too far off of what you should be doing in a lot of cases in this class. It always amazes me people come to an exam or even a final exam and never did an ice table after we did ice tables nonstop throughout the semester. So probably a good idea if you're asked to find some type of equilibrium concentration and pressures, that's probably the approach. So that is what we're going to do here. We're going to basically rewrite our reaction here. And we also could write our equilibrium concentration expression, which is our product, which would be Br. And once again, here we would square it because of the 2. We're going to divide it by the concentration of Br2, and that is going to equal lucky number 7 there in this particular example. Now we're going to start with our ice table. So initially, the only concentration given to us is Br2. So this is going to be 0.663. And because that is the only number given to us, we can again safely assume in this case that the initial concentration of our products is going to be 0. Any questions so far? Now, because again, we do not have any products, as we've been talking about, we can safely assume that this reaction is also going to basically proceed in this direction. So once again, here our reactants are going to be negative, our products are going to be positive. So the change here, which is represented by x, this would be minus x because the coefficient here is 1. This is going to be plus 2x because coefficient is 2. And once again, that is a product, so it should be increasing with time. To finish up the ice table here, we're going to just carry everybody down. I'm going to get rid of the molarity so it's not so busy in there. And that's going to give us 2x. First off, any questions on the ice table here? All right, so now we want to solve for x. So that is where our expression comes into play. And that means we're going to take our Br, which is 2x. So our k would equal our 2x squared divided by our products here, which would be 0.663 minus x is equal to 7. At this point, we do need to solve it mathematically. So we're going to multiply this to the other side. When we do that, also the top part gets squared. So that's going to be 4x squared is equal to 0.663 times 7 gives us 4.641. and that's going to be minus 7x. Usually when we do this, we want to get everybody to the one side. In most cases, the x squared, you can usually keep positive. You don't have to, but in most cases, people do that. So that means I'm going to move everybody over to the left-hand side. So that's going to give me 4x squared plus 7x minus 4.641, and that's going to equal 0. Any questions on that there? So this is definitely shaping up quadratic-like. And this is going to be our A. That's going to be our B. And the negative as well will be our C. So that's going to be our A, B, and C in there. So using our quadratic here, x is equal to minus b plus or minus the square root b squared minus 4ac divided by 2a. So putting our number in here, we're going to go with negative 7 plus or minus the square root. If you do what's inside the square root, that's basically 7 squared minus 4 times a times c. That will give you something like 123.256. And then if you take the square root of it, you will end up with something like 11.10. And that will then be divided by 2 times a, which is 8. So again, if you do the inside square root, you get 123 and some change. You take square root of it, you get about 11.1. That's going to give us our 2 answers for x. So I'm going to do the plus first. So that's going to be minus 7 plus 11.10 divided by 8. Going to give us an x value of 0.513. I'm then going to do the subtract. So minus 7 minus 11.10 divided by 8, going to give us a negative 2.26 or so there. Any questions on that there? Yeah. How did I get? I'm sorry, which one? I multiplied that to the other side. So to move what's on the bottom to the other side, you have to multiply it. So everything on the bottom there gets multiplied by 7. So 7 times 0.663 is this. And then 7 times x is that one. Yeah. Other questions? Okay, so clearly we're going to now take an x value and put it into these x values here. When I put this value in, what type of number do I get? If I took minus 2.26 times 2, gives us a negative 4.52. Can I have a negative concentration? No. So we know that this value is not good. That means that the correct x value here should be, in this case, the positive value. So because that is the positive value, we can now super zoom for some reason and go backwards. There we go. We can now put that correct value in. So we're going to take this 0.513, and that will give us our concentration of Br2, which at equilibrium is 0.663 minus x, gives us 0.663 minus 0.513, and that gets us 0.663 minus 0.513. 0.150, and we do need a concentration unit there, so molarity should reappear. Our concentration of Br at equilibrium, which is what this guy is, would be 2 times x, so that's going to be 2 times 0.513 and that'll be 2 times 0.513. We'll call it 1.03 molar would be our equilibrium concentration of Br. Question on that there? Any of the steps that we did there? So the 0.15 represents the equilibrium concentration of Br2. The 1.03 represents the equilibrium concentration of Br at equilibrium. Because this is math, we could actually check to see if we didn't screw up somewhere. Now, this one wasn't too difficult. There wasn't a lot of factoring going on or anything like that. How could I check to make sure I didn't screw up? I could check by what I just calculated were the equilibrium concentrations, right? So if I take those concentrations and put them back into this expression, they should equal 7 or 7-ish, yeah, with rounding. So if you do that, if you put back in there 1.03 divided by squared divided by 0.15, you get about 7, which is good. So I would highly recommend that if you have the time, you should throw those values back into the expression and make sure you didn't screw up somewhere. So if you put that back in, you got an equilibrium constant of 500, you definitely screwed up somewhere along the way. So it's a good way you could kind of check yourself. You will definitely not, in most cases, get exactly the value for K, but you definitely should be within the ballpark of just rounding difference, but you should not be super far away. So sometimes there's a lot of factoring that you got to do. There's a lot of numbers you got to carry over, and sometimes people miss it or something like that. So it's a good way at the end to make sure, hopefully, that you did it correctly. Any questions on any of those steps there? All right, I did one, you do one. Yeah, it's all right. Give this one a go here. Mixture 0.5 moles of hydrogen and 0.5 moles of I2 were placed in a 1 liter flask at 430 degrees Celsius. What is the equilibrium concentrations? Everybody there? The K value in this case is 54.3. So give it a go, see what you come up with. So obviously we're going to do our ice table here. We do need some concentration, so this is not too bad since it's basically divided by 1. So the concentration of H2 will equal our 0.5 moles divided by 1 liter, which will give us 0.5 molar. And we'll get the same thing there for I2 as it's the same calculation, 0.5 moles divided by 1 liter will give us 0.5 molar. Our equilibrium expression in this case will be K is equal to the concentration of HI, and we're going to square it, divided by the concentration of H2 times concentration of I2 is equal to 54.3 in this case. Any questions so far? At this point, we're going to do our ice table. So I'll do it right here. Why not? H2 plus I2 goes to our 2HI. So initially we have 0.5 molar. We got 0.5 molar of this guy. And again, we have 0 of our products. That again tells us that we are heading to the right there in terms of the reaction. So the change here will be minus X, and again here we're going to increase our products and do 2x, once again making sure we take into account those coefficients. That is going to get us, when we carry it down, 0.5 minus x, 0.5 minus x, and 2x. Any questions so far there? At this point, like we talked about, we're going to take everybody here on our equilibrium line and we're going to put it into our expression. So I'm going to do that on the next page here to give me a little bit more room, I think. So when we do that, we're going to take our, oops, there it is. So it's going to be our 2x squared divided by our 0.5 minus x times our 0.5 minus x And that's when we take our equilibrium line and put it in there. And that was 54.3, I believe. Yes. So at this point, we want to solve for it. So clearly, we don't want to do more work than we need to. So hopefully you could recognize that this is a nice perfect square with a big square root. If not, then you probably want quadratic, Bill, but which is fine. But you don't need to in this case. So that gives you 2x up on top, 0.5 minus x on the bottom. And the thing I personally always forget to do, actually take the square root there on the right. So let me try it this way, the correct way, 54.3, taking the square root, going to give us 7.36. It's good math practice if you did the other. It's all right. It won't kill you. At this point, it makes it much easier to solve for x, which, you know, I'm a fan of. So we're going to multiply what's on the bottom to the other side. So when we do that, that will give us 2x on the left. We will end up with a 0.5 times 7.369, something like 3.6845 minus 7.369x. We then want to bring the x back to the other side to combine them. That's going to give me 9.369x equals 3.6845. Then we're going to do a little dividing action there, yeah. So that's going to give me an x when I'm all said and done here of hopefully what I'm looking for, 0.393. Any questions on that there? So you don't always got to do quadratic, yeah. So, you know, don't overlook something that might be a little bit easier to do. If you went the full ride, by the way, you should end up with the same, hopefully. At this point, this x value will equal, if we go back to our table, all of the x values that we see in this table. And that's going to allow us to get to our equilibrium concentrations. So here, HI equal that equilibrium 2 times x, which gives us 2 times 0.393. And that is 2 times 0.393. 0.786, and we do need a unit of concentration there, a molarity. Our H2, I believe, was 0.5 minus x, gives us 0.5 minus 0.393. That's a 0.5 minus 0.393. Gives us a 0.107, also needs a molarity there. And lastly, our I2 should be the same since it was at equilibrium 0.5 minus x, giving us 0.5 minus 0.393, giving us 0.107. So these equal, obviously, the equilibrium concentrations of everybody at this point. Question on any part of that calculation? So as I mentioned before, there's a few different ways that you can solve these problems. And again, not all of them involve necessarily the quadratic formula. But again, if you do sort of take, since it is math, and if it's all correct math that you're doing, even if you took a longer approach, you should end up with the same thing at the end. Once again, here we could check our answers. If we take 0.786 and square it, divided by 0.107, and divided by 0.107, you should get somewhere in the 54 range, which I think we do. And again, that's a good way to sort of check to make sure you didn't screw up anywhere along the way. Any questions on that there? Any part of it? This is a calculation that you do a ton in this class. It's basically the class calculation right here. This is not one like I'll just figure it out later. You need to figure this one out sooner rather than later, because all calculations sort of go through this path of a nice table. Any questions on that there? All right, we will lay it up there for today.